Hello and welcome to the Greenbridge and BTG Intermediate Tissue Training module. In the first training module we heard about the different fibre types and the science of morphology, the major contribution to final tissue properties. We learned about the importance of blending and conditioning these fibres to get the most out of every single fibre. We learned about basic creping geometry, Yankee surface and blade metallurgy, and the impact on tissue quality of blade wear. We also learned about the importance of the Yankee cylinder and protecting it from damage and maintaining a uniform coating in the MD and the CD directions. In this module we will take a deeper look into the Yankee coating layers and the importance of stability by continually refreshing the coating layer. We will also look deeper into the dry crepe process and the parameters that affect the creping process long before you might imagine. You will also find some examples of new ceramic and steel creping blades and also some worn, damaged and heat affected blades in the display cabinets. So please pause the training at the appropriate moment to take a look. So, controlling to a stable and accurate consistency before refining and at the basis weight valve is critical to our process and finished product. The first machine stage after stock preparation is the headbox and forming section. Thin stock to the headbox can be either homogeneous or monolayered or multi-layered. Monolayer machines blend fibre together usually at the pulpers or a dedicated thick stock chest. Usually this means that input fibre is co-refined. Layered machines making soft tissue mostly divert eucalyptus to the side of the sheet in contact with the Yankee and Yankee coating for maximising softness. Usually they have separate stock and refiner streams, but could share a common pulper for batching softwood separately to eucalyptus. Fibre is the most expensive raw material, accounting for more than 70% of the cost of production. Therefore, fibre selection and protecting yield is always in our top priorities. As a reminder, length and width are drivers for tensile and bulk respectively, with fibrillation index an important refining consideration. Managing kink and curl helps strength as well as stretch, whereas softness is driven by lowest fibre coarseness, coupled with a stable and well-managed creping process. Controlling these parameters proactively in the stock approach to model tissue quality is a key objective for BTG's Data Park contribution to Industry 4.0 in tissue. Historically, we tend to alter process and creping parameters and/or fibre blend and refining, respectively, following QC tests on the finished sheet, hoping to catch the next reel. This approach has served us well, but inevitably adds to the coefficient of variability. Here is a diagram of a typical headbox. The basic function of any headbox is to convert an MD pipe stock flow to a uniform CD, MD and Z direction fibre distribution to maintain fibre suspension, dispersion and jet turbulence levels, and hence to establish paper properties such as formation, fibre orientation, MD, CD tensile. This is a triple layer headbox represented by the red, orange and yellow layers. Usually short fibre would be diverted to the Yankee layer and the longer fibre or perhaps cheaper fibres to the middle layer or felt layer, sometimes called the non-Yankee or hood layer. Lamination also adds intrinsic strength to the sheet. During converting, 2 or 3 sheets are often wound together with Yankee layers on the outside surfaces for hand feel. Here we see the internal drawing of a similar headbox, but with 2 and not 3 layers. A tube bank from a tapered distribution pipe maintains an even CD flow, hence even CD fibre distribution and weight profile. To maintain laminar flow and to keep the fibres apart, there are a series of hinged polycarbonate or Lexan sheets in the headbox, which taper towards the outlet of the headbox or slice. The stock is fired under pressure from the adjustable slice lip between the felt and/or the forming fabric or wire, which wrap the forming and breast rolls respectively. So, after diluting wood pulp to isolate every single fibre to generate a good sheet formation, the rest of the process is all about taking that water out again. The first step is the former section, of which there are 4 main types. The most common is a crescent former, where the thin stock jet is directed between a forming fabric that promotes drainage and a felt. The sheet path is shown by the red dotted line. The second most common is the twin wire former, where the stock is directed between two wires. These twin wire formers are usually referred to as a C-wrap or an S-wrap former, the letter depicting the path of the sheet around the former and breast rolls. Top left is a C-wrap, the bottom right an S-wrap. Not so common is a suction breast roll former, where dewatering is exclusively through a wire. Likewise, a Fibre former, which is old technology, is limited to older machine conversions and drainage again through the wire. In LDC, whatever the headbox configuration, the sheet is supported to the press section by a felt. Therefore, keeping the felt clean through showering is a vital component of any light dry crepe machine. Former section drainage would normally dewater thin stock from less than 0.5 consistency to 12 to 15%. Vacuum dewatering on the felt will then increase the consistency to the range of 20 to 25%. Dewatering through the suction press roll will then increase consistency at the press nip to approximately 40%. This is an important consideration for sheet drying energy and for Yankee coating setup. At the press, a constant and uniform CD linear load presses the sheet through the felt into the Yankee coating. The linear load, or how hard we press the sheet, and the press configuration can affect dewatering and also tissue properties, especially bulk, absorbency and stretch. The basic functions of the press or pressure roll are to mechanically dewater the sheet, to transfer the sheet to the Yankee, and to initiate the intimate contact between the sheet and the Yankee coating and cylinder. The press or pressure roll comprises of the components we see, the journal and bearings which allow the press body to be fixed to the machine frame, allowing the shell to rotate, and the components we do see, those that do all the work. The suction or vacuum zones of the press dewater the sheet into the felt before entering the nip. The vacuum zones are covered by the machine drilled roll shell. The roll shell is covered by a polymeric roll cover, for example polyurethane or other rubber compounds. A hard roll cover offers higher nip pressure, better dewatering and higher tissue strength. A soft cover offers lower nip pressure, longer nip contact with higher tissue bulk and thickness, but better compatibility with the Yankee. Each press roll cover is pre-ground to match the crown on the Yankee when it is at full steam pressure. These roll covers also must be hard wearing and resistant to external and internal forces, to heat and also to chemical degradation from process and cleaning chemicals used on the paper machine. In LDC we generally see three types of press configuration. The suction press roll, which dewaters and presses the sheet through the felt and onto the Yankee at approximately 40% consistency at the nip. A double press configuration comprising a standard suction press roll followed by a second press or a blind drill press, meaning the sheet is pressed twice through the felt onto the Yankee. A double press is particularly effective for producing low bulk products. Some newer machines have an extended nip or shoe press. The shoe press extends the length of the nip. Prior to the shoe press we will have a suction dewatering roll. A lower shoe press load gives lower post-pressure roll consistency, meaning a wetter sheet at the nip. This leads to highest bulk softness and maximum fibre savings. A higher shoe press load gives higher post-pressure roll consistency, meaning a drier sheet at the nip. This leads to highest hand feel in terms of smoothness and highest energy efficiency but lower bulk. Shoe press machines can facilitate better creping efficiency through generating higher MD stretch, allowing lower crepe ratio, hence higher rail speeds and increased productivity. There is of course limited space available to fit in one or two presses or a press and a suction roll and still take maximum advantage of the full drying capacity of the Yankee circumference and hoods. Therefore the dwell distance between the press nip and Yankee coating shower is at a premium. This is important as this area is the evaporating zone. where the applied coating is dehydrated and partially cured prior to the sheet being pressed onto it. The time taken for this zone to move around the Yankee is called the dwell time. Some machines can also have a steam box to help dry the sheet onto the felt and also help with the CD profile. After pressing, we have removed as much water by drainage and vacuum as we can, meaning the rest is removed by evaporation. This is the most expensive way to dewater, and after fibre is the second highest cost of production. Evaporative drying dries the sheet from 60% moisture to anywhere between 2 and 5% final moisture. There are two processes which combine to facilitate this drying process. Pressurised steam increases the Yankee surface temperature to about 80 to 90 degrees C to dry the sheet, and gas burners in the hood surrounding the Yankee heat outside. Yankee cylinders are traditionally cast iron but can also be steel, which are factory metallised. Cast iron is a relatively soft and porous material, so the surface can wear quickly, requiring it to be ground periodically, especially if the wear is uneven. After each grind, the shell thickness is reduced. Eventually, the thickness reduction reaches a critical point called the D-rate point. This means the working pressure of the Yankee and/or the linear load of the press must be reduced to run the Yankee safely. This reduces machine capacity. The answer to this is metallisation, when an alloy layer is welded around the Yankee surface, but before the D-rate point is reached. The metallisation surface is less porous and harder wearing than cast iron. Therefore, fewer regrinds are required, provided supplier recommendations are followed for looking after the metallised surfaces. So steam is fed into the Yankee cylinder anywhere between 4 and 12 bar pending the design. It condenses and the resultant heat transfer heats the shell, which then dries the sheet. Condensate must be evacuated from the cylinder at the same rate as it forms to prevent waterlogging and to maintain an even MD and CD temperature on the shell. The inside of the Yankee shell is ribbed or grooved in the MD direction. As the Yankee rotates, the condensate is collected from the grooves by soda straws. Condensate then flows into the headers, along with some steam due to the difference in pressure. The number of headers and straw assemblies depend on the Yankee diameter and are equally spaced around the Yankee shell. The riser pipes carry the condensate away from the headers to the central steam collection pipe to the condensate handling system. Differential pressure is used to control the velocity. That's either the straw tip or the blow-through velocity you will hear, at which the condensate is removed. This differential is vitally important for maintaining an optimal and stable MD and CD shell temperature. Keeping the Yankee internals clean and free from corrosion, deposits or scale is also vitally important, not only from a safety aspect of a pressurised vessel, but any blockages in only a few straws can lead to cold spots on the Yankee, giving non-uniform CD and MD drying. This can lead to issues with Yankee surface health and uniform shape and topography issues. A Yankee hood system comprises the dry end hood and the wet end hood. These are flexibly joined and are lowered to dry the sheet with hydraulic jacks or raised when the sheet is off. Air supply fans pull in fresh air and combine it with hot recirculated air, which is then fed to the gas burners. These burners heat the mixture to the target temperature. Supply fan pressure blows the hot air into the intake duct of each hood, into each header across the full width of the hood. The hot air blows through the supply header and profiling dampers. Through nozzles or holes called a blowbox. Profiling dampers control CD airflow and enables you to target CD zones. The supply fan speed controls the flow of air to each hood and hence air velocity contacting the hood side of the sheet. The CD hood dampers are usually manually set by the operators, depending on the moisture profile being obtained. Some machines can take feedback from the moisture scanner and automatically control the CD damper positions based on this feedback. The balance between drying through the hoods and drying on the Yankee is referred to as the Yankee hood drying bias. Yankee drying is considered lowest cost, but too hot a Yankee can also lead to sheet blistering, the sheet sticking too fast to the Yankee surface, and also to hard coating. On the other hand, excessive hood drying increases cost and the risk of fires, especially in a dusty environment. Finally, and assuming we have everything in optimal control in stock preparation, refining, consistency control and wet end chemistry, and processes 1 to 4 on the machine, we have the creping process. We learned a little about this in Module 1, and we are now going to dive deeper into the process and what affects the process of creping. So, this is familiar, the creping objective, to be executed safely in a controlled and stable manner, protecting the Yankee cylinder surface. As the sheet dries around the Yankee and the hoods, it is kept in place by the Yankee coating. The sheet is not or should not be in contact with the Yankee itself. It should be stuck on the softest part of the Yankee coating matrix, i.e. the freshly applied layer and the soft substrate, and not the hard cured coating layer protecting the Yankee. We will learn more about this in the next slides. Optimum creping is then a succession of microfolds formed after the initial fold is forced out of the coating pocket by the creping blade, i.e. stage 1 and 2. Microfolds build up on top of the creping blade until they naturally grow too large and exit the blade as a macrofold at stage 4. Crepe ratio, that is the difference between the Yankee and reel speeds, allows this process to develop naturally. In the diagram here, we see 3 simple adhesion models. The dark grey vertical line in each diagram is the Yankee, or to be precise, the hard protective layer of coating protecting the Yankee surface, whether it be cast iron or metallized. The thin black line is the sheet, and the red dots depict adhesion, or adhesion points. These adhesion points are provided by the Yankee base chemical or adhesion aids and pulp extractables carried forward in the wet sheet. The more red dots, the more adhesion. This can be either from the coating chemical addition, as we've said, and the type, or from the hemicellulose containing pulps. The black rectangle represents a creping blade. The red folds or crepes below the black blade represent the crepe pattern achieved under each adhesion condition. You can see that low adhesion leads to a coarser crepe, higher bulk and lower softness. And high adhesion generates more crepe bars per centimetre, leading to a more densely crepe sheet, which gives higher softness and lowest bulk. The sheet is folded between adhesion points into the macrofold. At very high adhesion levels, the sheet explodes, causing bulging rather than folds. This is a slide from the basic training showing the contact angle, also known as the sliding wear angle. This is also close to what we call the blade holder angle. We also see the blade bevel angle, the take-off and creping pocket angles. Increasing the pocket angle increases softness and reduces bulk, and vice versa. When any blade wears, whether it be steel or ceramic, both the tip impact and the sliding wear angle reduce the size of the pocket angle. A machine can have a minimum of 2 and maximum of 3 blade holders. One of these positions will always be the creping doctor holding the creping blade. The cleaning blade will smooth the remaining coating before a fresh application of coating spray is applied. The cut-off doctor removes the sheet at either a crepe blade change, grade change, a break or a wash-up. If there isn't a cut-off doctor, the cleaner blade will perform this function. Each blade sits in its own blade holder, which is set up to make a specific contact angle or blade holder angle with the Yankee tangent. If this angle is too low, the sheet takeoff can be compromised. Too high, and the blade can be too aggressive against the coating and cylinder and potentially cause chatter and damage. Usually the creper has the lowest blade holder angle, enough to cut through the sheet and crepe with good sheet control, but not too high an angle so that it induces chatter. The cleaner blade holder angle is usually higher and the cut-off angle higher still to ensure efficient cutting through the sheet. Stick out is the distance the blade protrudes from the blade holder jaws or between one jaw and a backing blade. Typically this will be between 15 and 25 millimeters. The longer the stick out, the more the blade will bend, reducing the blade holder angle by 1 or 2 degrees. The shorter the stick out, then the less bend, and the angle remains closer to the setup. On a lot of blade holders there is a facility to increase or decrease the stick out without altering the blade dimension by using a step-up ladder or step-up strip. Having the necessary piston travel to contact and load against the Yankee should always be ensured before trying this. Each blade holder will have a pressure gauge on the pistons which push the blade holder to the Yankee cylinder. Some rigid holders rely on this pressure to apply the linear blade load. Most these days have a gel, an air or an oil-filled tube running along the length of the tip of the blade holder to ensure that pressure is evened out along this, or that even the final loading pressure applied here. Having an even profile across the full width of the machine is essential. Blade holders often have a series of manual relief or load nuts on the front and back edges to enable edge issues to be assisted by relieving or increasing load locally at these edges. It is, however, not the pressure which is critical measure on a blade holder. This would be the linear load across the blade measured in PLI, kilonewtons per millimetre or newtons per millimetre, which must be converted from pressure in bar, pounds per square inch or kilopascals. Each blade holder will have its own conversion chart which can be made by taking several measurements of the holder and converting it to a loading curve. But let's not forget, creping is not just about product quality and achieving the three-dimensional sheet structure. In addition to sheet quality, creping is also about protecting the Yankee dryer, either the cast iron shell or the metallization, and maximising machine productivity through either achieving stretch and bulk at maximum reel speed, hence lowest crepe ratio, or from maximising machine efficiencies through the lowest number of breaks and the maximum uptime. Together with achieving optimum and consistent sheet control within specification, these are the three cornerstones a robust Yankee coating and Yankee management system must deliver. Some LDC machines will have 2 coating chemicals, others may have 3, occasionally 4. TAD or structured sheet machines may even have 4 or 5. Each component is metered according to the speed and the width of the Yankee to a measure of milligrams of active chemistry per metre squared of Yankee coverage, taking into account product solids, their specific gravity of the chemical. The chemicals are mixed together with water at approximately 50 degrees C, mostly to prevent microbiological deposition, either in a tank or in a line, and sprayed onto the Yankee cylinder after the cleaner blade and before the nip. The spray bar will have several offset but equally spaced nozzles, with or without oscillation, designed to provide triple overlap, hence a consistent spray pattern to ensure full sheet width optimum CD coverage on the Yankee. The type of nozzle, spacing, distance from the Yankee, oscillation rate if any, sheet width and pressure are all taken into consideration. The water evaporates and the coating layer develops on the Yankee surface to accept the wet sheet at the nip. One function of a base coat is to adhere the sheet to the Yankee to ensure close intimate drying on the cylinder, good sheet control off the Yankee whilst maintaining and generating crepe bars when the sheet is forced off the Yankee by the creping blade. Its other function is to develop a hard layer to protect the Yankee surface from erosive and corrosive wear and also adhesive wear, sometimes called micro welding, from heat and friction generated by direct contact with steel from, example, a steel creping blade. Base coats are polymers, for example derivatives of polyamine epichlorohydrin resins, or polyethyleneamine. Each product type will dehydrate but become tacky at different temperatures. The temperature at which the polymer transitions from a fluid liquid to a solid and is at its tackiest is called the glass transition temperature, capital T, small g. The base coat will reach glass transition before the nip on the tissue machine and then must re-wet. That is, it becomes tacky once more with the contact from the wet sheet to accept the sheet onto the coating layer. The function of a release aid is to control adhesion by interrupting the adhesive network and suppress the glass transition temperature, thus extending the re-wetting window. Release also lubricates the blade, reduces blade friction against the coating layers, and then releases the sheet from the Yankee, helping to generate stretch as the release migrates to the sheet side of the coating over the Yankee cylinder. Many release products are oil-based. Mineral oils are becoming less popular due to environmental profile, but generally give very good stretch response. Vegetable oils and synthetic derivatives are becoming more popular, although the release effect can be finite per product, pending other conditions and of course the base coat it's in use. Quat-based debonder type products are also popular. These can give very good release, soften the coating a lot, and also transfer to the sheet, providing surface softness. Rheology modifiers soften or plasticize the coating, altering its film flexibility, often retaining moisture. Using them can enable us to develop a thicker but soft coating layer without making the coating go too hard, which is thought to encourage bulk and bulk softness and improve doctorability and coating refreshment. Phosphates are added for Yankee protection to provide a key on which the base coat can more easily adhere, thus increasing coating to Yankee bond efficiency. Monoammonium phosphate or diammonium phosphate forms phosphate ion complexes on the Yankee surface, which passivates and protects the Yankee surface and can actually repair some small areas of localized damage. Its use is always recommended when the old coating layer has been stripped, either intentionally at a polish or a regrind, or unintentionally through a process or chemical blip. Organic phosphate chemistry is very complex, but sometimes these are used in niche applications, for example in TAD. When using phosphates, high hardness in the spray bar can lead to nozzle blockages, so there is a trade-off between having the desired amount of calcium and phosphate salts. It should be stated at this point that having an acceptable surface roughness and CD uniform roughness on the Yankee surface is also a very important factor for ensuring a stable and reliable coating. Additionally, uniform coverage of the Yankee coatings is essential. Ensure the full sheet width has equal coverage. That means 0 blocked spray bar nozzles. After a couple of weeks working in a tissue mill, most people would tell you that a Yankee coating consists of a base coat, a release oil, some MAP perhaps, and maybe even a modifier. That is correct, but not the full story. If we could take a cross section through what would be an ideal Yankee coating, these are the layers we would want to see. On top of the Yankee shell and any metallization layer would be an inorganic substrate made up of minerals and salts, either naturally there from the spray or process water source. These would be calcium carbonate, iron and magnesium salts. They could also be deliberately placed there, for example by phosphate addition, and by the ion complexes it forms with the surface of the Yankee, or the metallization. On top of this, we would see the cured coating layer, which protects the Yankee from corrosive and erosive wear and restricts the metal blade to metal Yankee contact and subsequent adhesive wear. This is made up of cured base coating, not initially removed by the 3 doctor blades, which has also attracted paper making components and contaminants and baked on the surface of the Yankee to form a very hard protective layer between the Yankee substrate and the more recently applied coatings. Then we have the soft and hopefully robust organic top layer, or coating layer, usually made up of what we see on the previous slide. Base coat or adhesion aid with possibly a built-in modifier, some MAP maybe, and a release agent. Most machines will fix the addition of a base addition and MAP and use the release to control adhesion, stretch and sheet control. Because the sheet is still 60% moisture at the nip, this water contains residual pulp contaminants and process and functional chemicals which will also be taken into the coating. How much is taken in depends on the efficiency of the chemical and the solids equilibrium management by the machine. Most of this, over time, ends up in the hard cured coating layer. Coating itself establishes and undergoes several disruptions during machine operation. For example, creping blade changes strip coating back as a new sharp blade removes more of the cured coating layer than the previous worn blade was doing. Chemical cleaning of felts or system cleans or wash-ups, even high sheet moisture, can wash coating off the Yankee cylinder. Additionally, changes in process conditions, chemical additives, water usage can alter the concentration of contaminants impacting the organic coating. It is important to understand the process and proactively manage and centerline wet end, chemical add-ons, blade management and all other influencing factors to keep coating as stable as possible with as few disruptions as possible. Now we have established there's more to Yankee coating layers and composition than meets the eye, so we can begin to understand some of the complexities. We control Yankee applied chemistry to a specific amount of milligrams per square metre by product grade, usually fixing base and altering release to control sheet adhesion and sheet control off the blade to meet end product specification, to help rebuild and to avoid slack edges which can lead to breaks. The applied chemicals give us sheet adhesion, release and build cylinder protection. Different polymer types and combinations behave differently due to varying glass transition temperatures, molecular weights and elasticity. We also have what is termed natural coating or process contamination, which is everything that contributes to coating or release that we can't easily control. Having better or online instrumentation and data visualization resources such as DataPark and other historians can help us better monitor and control what goes on at the wet end. Not being to scale, we can see here the different components that can potentially contribute to coating and in time make up the combined coating layers. Each has a role to play in the holistic process, but each must be controlled as well as possible. The blue segment of the overall coating makeup is what we can monitor and control. The red segment, which is a lot more difficult though not impossible to monitor and control. What we change in the blue segment is often a result of changes or in the magnitude of the red segment. Now we see the Yankee applied coating cycle as it plays out on the Yankee cylinder. In this instance with 3 doctors and a suction press roll configuration. The first zone after the coating is applied via the spray bar is the dehydration zone, where the spray carrier water is evaporated by the Yankee surface heat to leave behind the coating mixture in a micro layer on the cured coating above the Yankee surface. The glass transition zone is the area on the Yankee where the adhesion aid or base coat transitions from a fluid liquid through a tacky phase before solidifying. Each polymer having different and quite wide-ranging glass transition temperatures. You will also hear terms from suppliers such as cross-linking and pre-cross-linked and even dehydration polymers. Don't panic. Cross-linking simply means polymer chains reacting with each other to form multi but micro-layered matrix. Traditional polyamine epichlorohydride resins or wet strength resins cross-link, and the process is accelerated by heat, high pH and slowed by conditions of low pH, high chlorine, high oxidizers and colder conditions. This can be useful information to know. Pre-cross-linked simply means that the cross-linking reaction happens in the production plant of the chemical supplier. Products can also be partially cross-linked, which is when the cross-linking reaction is stopped by adding either caustic or acid partway through the production process. Hence, base coats can be alkaline as well as acidic. Dehydration polymers are not cross-linking, they simply layer on after all the associated water has been evaporated off. Examples could be polyethyleneamine and polyvinyl alcohols. Next is a press nip and re-wetting zone. It is important to build in a little flexibility at this point as the glass transition phase cannot easily be controlled or even predicted. So the polymers we use must be what we call re-wettable. This means that the moisture from the sheet being presented to the coating reactivates the polymer layer's adhesive nature and accepts the sheet into the coating. The time it takes for the Yankee cylinder to rotate from the spray bar impact to the nip is called the coating dwell time, and is an important consideration in how quickly the spray water evaporates and where the coating becomes tacky. Machines will have different dwell times, and the same machine can even have different dwell time with any significant changes in Yankee speed. We then come to the main area of the Yankee and Hoods where the sheet drying occurs. At the same time, the coating layer sets and becomes harder, but hopefully still pliable and flexible so that the blade glides in it rather than bounces off it through the sheet. The cut-off doctor will be raised at this point, and at the creping blade the sheet is creped off the cylinder, the blade sitting through the sheet partway in the set and flexible coating film. The release oil added to the coating mix by this time will have migrated to the sheet and coating interface to help the sheet release from the Yankee and build and stretch. Finally, if there is a cleaner blade in use, the cleaner levels off the coating debris left behind. Some residual coating and contamination will become baked into the hard coating layer each pass. The level coating layer is then in a better condition to accept a fresh application of coating from the spray bar, and so the process repeats. If we now consider the addition of natural coating or process contamination to our coating model, Yankee applied coating is the blue segment and applied at the spray bar, with the red portion being the coating contamination inherent in the wet sheet presented to the press nip. At the nip, the sheet is approximately 40% solids, meaning 60% backwater, and so with a level of process contamination. Some of this contamination is removed at the press through the felt. The coating products are predominantly cationic at this point, which means they are positively charged and tacky. The contaminants are anionic or negatively charged, meaning there is a natural attraction into the coating matrix. This diagram represents what we call the Dreshfield effect on a flattened out Yankee surface. To the left is the nip and to the far right the creping blade. The sheet could be 10 to 20 fibres thick depending on the fibre blend or the mix, and also depending on the grammage and the bulk. The red dots are the fines, fibres, fibrils, colloidal material and other contamination which will have cycled up in the backwater and become presented at the nip. We can also see the various coating layers which we have discussed in previous slides. As the sheet dries around the Yankee, the water is evaporated, but the contaminants are left behind. They can't go anywhere else when the drying is exclusively evaporative. The contaminants will migrate to the hottest part of the sheet as shown. Some of the contaminants may be chemically fixed or retained to the individual fibres to stay within the sheet. This is where the drying bias we have discussed earlier is important, as more contaminants will tend to migrate to the hotter side of the sheet. So, some will go to the hood side and some to the Yankee side. The ones that go to the Yankee side will become stuck in the coating, eventually trapped in the coating matrix as it cures. Fines and other contaminants then add to the cured base layer, which can also make it become very hard very quickly and less flexible than just a hardened but flexible polymer base. If we dig deeper into what happens at the creping blade, we see the layers again, the drier surface, the metallization, inorganic substrate, and then what we are really interested in on a daily, if not hourly basis, the hard cured coating layer and the more freshly applied organic coating layer. The hard cured coating is residual coating chemistry and paper making contamination as we've discussed, and the orange layer more flexible, hydrated and robust organic coating, which has gone through the glass transition and stuck the sheet to the cylinder. The blade sits in this layer, having cut through the sheet when initially applied, and crepes the sheet and removes it, or refreshes some coating rather, from the cylinder. The blade is the black object to the bottom left. If we imagine the contamination levels increasing in the backwater, then more contamination will be taken into the coating and migrate into the cured coating layer. This layer will then grow. On machine we see it as the coating layer becoming more opaque or heavier. Blade vibration usually increases, and we usually hear it too as an auditory change. If this layer grows too big, then it moves closer to the blade, which can sometimes be controlled by running very high levels of release. Once the blade starts contacting this hard cured layer, it starts to bounce along rather than glide in the soft layer. Sheet defects such as picking or holes follow, as can breaks, especially at the edges where the web is more prone to breaks. Worse still, the blade can dig into the coating, maybe through the coating, leading to chatter in the coating, or worse still, the Yankee surface, which should be avoided at all costs. It is therefore important that the controllable and deliberately applied Yankee coating dominates over the less controllable hard cured coating layer, while still maintaining a sufficient cured coating layer to protect the Yankee cylinder. And here we can see the steps that lead to chatter when coating becomes too hard. On the left we can see the blade gliding in the organic coating underneath the sheet, so removing some coating and the sheet and crepe structure. This is what we want. The creping doctor linear load is sufficient to comfortably overcome the sheet, the adhesion and Yankee forces, and gently go about its business of refreshing the coating and creping the sheet. Provided the coating remains soft and robust, then it's happy days for any blade material. However, then we go to the top right, and the cured coating layer, or the coating itself due to the release being too low for example, has started to become hard and or dominant over the soft robust coating. The hard coating and resistance from it to doctor pushes the blade out of plane and momentarily away from the Yankee. The blade skips out, but loading and mechanical forces prevent any further out of plane movement, and the blade then accelerates downwards into the coating layer once more, hopefully stopping before it penetrates through to the Yankee surface. This happens so quickly that it repeats and resonates in millisecond intervals, and you end up with a band of chatter. Depending on how CD uniform the coating rheology is would dictate the CD extent of the chatter. Here are two examples of what we don't want to see on a Yankee cylinder. Edge chatter on the left and full width chatter on the right. By measuring the wavelength of the chatter marks and knowing the speed of the Yankee, the frequency of chatter can be calculated and related back to events. For example, edge related issues, full coating related issues or higher frequency rather, or mechanically induced chatter marks at low vibration frequency. Edge deposits and edge chatter are more commonplace than full width chatter. Edge contamination tends to happen from the overspray of coating or from jet capture from the headbox transferring from the felt to the Yankee, coupled with getting the edge relief correct on the blade holders. CD chatter marks will manifest themselves as coating coverage issues, both MD and CD, eventually leading to breaks, sheet defects, for example holes or chatter defined marks in the sheet. Once there, chatter will not improve of its own accord and will only get worse. If the chatter is limited to the outer layer of the cured coating layer, it can often be removed by additional use of the cleaner, potentially with a higher addition of release to strip the coating back, or even from a caustic felt wash. If chatter is deep in the coating, one way to remove it is to oil and doctor the cylinder to remove the coating layer and then apply a screen cloth or emery board under load for a few hours. The time will be determined by the severity of the chatter. You should replace the emery or screen cloth as it clogs up. The cylinder should then be remapped and reconditioned every time before starting up. If the chatter penetrates even the cured coating layer into the Yankee or metallized surface, then a doctor back grind or regrind may be required. This removes some of the cast iron or metallization, so reduces the lifetime expectancy of the Yankee shell or metallization. Metallization is only at most 1 mm thick, so there aren't many regrinds in this layer, hence it is vital to avoid surface chatter. As you can imagine, chatter can quickly become a very costly issue from an operational and maintenance budget perspective. Remapping and reconditioning to provide an initial protective layer is imperative. So, a reminder, blue segment. Coating from the spray bar, which is hopefully applied in a controlled and CD even manner with a stable operation. It controls the sheet onto and off the Yankee, protects the Yankee and helps to achieve product specification and blade lifetimes for as long as safely possible. It needs to dominate and augment any natural coating coming from the tissue making raw materials. Red segment. The red segment is the wet end contamination, or more kindly, natural coating. We have significantly less control over this at the nip than in the wet end and furnish. Natural coating can help coating, especially insoluble hemicellulose from pulps. Even the calcium carbonate from de-ink pulp, from a pH and a chemical perspective, can help coating. However, if the natural coating dominates over the organic coating and increases the cured coating layer significantly, it will eventually lead to hard coating if other conditions align. Which brings us on to hard coating, the tissue maker's nightmare. Coating needs to be adhesive, tacky and robust to achieve sheet QC specs, and then be flexible and tough in the cured coating layer to protect the Yankee from erosive, corrosive and adhesive wear. Once the coating becomes too hard, the blade stops working in the coating and works against the hard coating layer. Hard coating also makes blades wear faster. Steel will wear faster, of course, than ceramics or carbide blades. High performance blades are a proven successful tactic against hard coating and are more forgiving than steel. However, using them is not usually addressing the root cause of the issue. Here we have a table collected from data across Europe over several blade analyses, detailing the type of high performance blades currently on the market. Experience, blade analysis, material science and machine monitoring proves that high performance blades wear slower than steel in any coating conditions, and more so in the more unforgiving territory of hard coating. There are several different ceramic and carbide materials which also wear differently and can be matched to specific machine coating and sheet QC requirements. Higher blade lifetime means less frequent disruptions to coating and to sheet stability and machine setup and production, hence a commercial success for almost every tissue machine over steel blades. So the coating makeup pie chart on the left is what we would normally see from an LDC machine. Using BTG's trash balance survey, we are able to semi-quantitatively calculate the percentage of coating contaminants to the overall combined coating add-on, and based on our collective monitoring around Europe, would recommend a Yankee coating contamination factor of less than 75% to be a safe figure when considering potential hard or unresponsive coating, which could lead to issues including chatter. Usually, however, once the coating is set up, a machine will cope with a higher but stable percentage of trash presentation to the coating, stable being the operative word. Usually this will be achieved by applying a minimum 2.5 to 3 milligrams per square metre of a modified base coat, with at least twice that of an effective and responsive release to help soften the coating layer and lubricate the blade against any hard coating layer, which could or is becoming too dominant. Often, issues arise when 75 or 80% Yankee coating contamination factor quickly becomes 85 or 90 or 95. This could be a result of a furnish change, i.e. a higher fines containing furnish, a lower grammage with poorer natural retention, a blip in the natural or chemical induced retention mechanism, for example starches or wet strengths or even polymers added deliberately. Variable recycle from a DAF or a recovery filter could have the same effect, as could a sudden reduction in water consumption or a problem with the clarified water system. If the solid's equilibrium, hence the Yankee coating contamination factor, flips back suddenly or gets worse, this will likely affect coating, unless of course there is online instrumentation to pick up these changes in whitewater stability or total solids quickly to enable a proactive correction or coating changes in advance. Provided we can avoid these flips, then most coating products these days, once set up, are pretty robust. So stability is really the key to a nice robust coating, which is the key to getting the most out of your blades, regardless of their metallurgy. Yes, harder blades will deal better with harder coating, but having a soft, robust but responsive coating is always the first objective for any blade material. To the side of the coating component pie charts, we have a non-exclusive list of the process and machine variables that can influence both organic and natural coating setup, efficiency and hardness. Moving something in one direction can make it too hard, moving it in the other make it too soft, both of which bring about different problems. Being able to fix and centerline as many of these parameters as possible takes away a lot of problem-solving headaches if things go wrong. More about this in the advanced section, but for now, having a handle or control on as many of these variables as possible is preferred. If they can be tagged and traced on the DCS system or via a data historian linked to the coating KPIs, then so much the better. We will learn more about vibration in the advanced section, but blade tip vibration is an excellent and now well accepted measure of coating hardness. Vibration can quickly determine if coating is becoming too hard, and the different frequencies from 0 to 24,000 Hz can be measured to assist the user interrogate his DCS system and coating settings to establish what has changed and what needs altering to regain coating film integrity at the desired vibration amplitude. So here we see what we don't want to see: chatter and adhesive wear. Maintaining an optimum and stable coating is a vital and important consideration for the tissue maker. It makes and breaks the three cornerstones of creping: quality, asset protection and productivity. If coating is too hard, it presents the ideal conditions for chatter marks to develop. Hard coating does not necessarily lead to chatter marks per se, as it can be managed effectively with, for example, high performance blades and regular vibration driven blade changes, well maintained set of doctors and optimum coating coverage and blade lubrication. Again, please note 0 block nozzles. However, if you have hard coating and other parameters are not quite right, then the risk of chatter is significantly increased over having a soft robust coating with the same out of center line parameters. On the other hand, if coating is too soft, wet or streaky, then you should see sheet control issues as an early sign. Floaty sheet may be felt following, perhaps even blistering if the Yankee is also too hot. This could be a result of too much release and not enough base coat, a chemical wash perhaps, or simply a high sheet moisture, either fully CD or just a peak washing the coating away. Even a combination of these. It is possible that if there is metal to metal contact because of limited coating, then adhesive wear can also occur when coating and coating barriers have been washed away or removed. Adhesive wear or micro welding is a transfer of metal from the Yankee to the blade, which leaves holes or ND lines in the Yankee surface and must be avoided. Using a ceramic blade significantly reduces the risk of this over a steel blade on any Yankee surface, and another reason high performance blades are preferred over steel. The final picture is actually one of a steel blade in contact with the dryer when coating has been washed away. The bits hanging at the bottom are actually part of the Yankee cylinder surface being transferred to the blade by adhesive wear or micro welding. And so to finish with the cornerstones of creping and why we use high performance ceramic or carbide blades. They are proven to enhance asset protection through less Yankee wear and damage, including adhesive wear. As such, fewer regrinds are required, which is important on a cast iron Yankee, becomes more important as the shell thickness is reduced, and is massively important on metallized surfaces. In terms of productivity, there are significantly less blade changes, meaning less UTM and more machine uptime. Better and more stable coating over longer periods makes for fewer breaks, so less downtime and less settling in time and slab waste. Because the machine is more stable for longer, the coating more stable for longer, and the blade tip keeps its edge for longer, there is more available time to work on the coating, the process and the blade management to optimize the machine and the quality. Longer lifetime, high performance blades tend to generate more stretch, so enable lower crepe ratio, hence faster reel speeds. Higher and stable bulk and stable softness at higher moisture means the machine can run at higher yield and lower drying energy for the same air-dry grammage. Converting can take advantage of higher stable bulk, avoiding oversheeting in roll packs. The savings in terms of fibre costs in this instance can run into hundreds of thousands of pounds or euros per year for the machine and converting operations. In terms of sheet quality, high performance blades provide enhanced softness over extended periods. The same for bulk, stretch and sheet structure. This gives the converting operation more confidence in the product and set the converting machines up to run less waste with faster throughput with less breaks, joins, reel dressings at joins, etc. Converting is also where the real value is added to our tissue product, and perhaps the savings made in this area from stability and enhanced runnability are often understated. So, this is the end of the intermediate training on tissue and creping delivered by Peter Greenwell of Greenbridge Consulting on behalf of BTG. Please feedback any comments and thank you for your interest and attention.